In this video, I'm going to be explaining graphs of derivatives, or derivative graphs. A derivative represents the slope of a function or a graph. So the graph of a derivative is going to be a graph of slope values. We can estimate slopes and just visualize it, or we can actually find the derivative function and evaluate it at certain points on our graph. Let's start off with an easy example here, a linear function, negative 3x minus 4. That's a decreasing linear function. Its graph is represented by this pink line right here. We know that the slope of that linear function is negative 3, and it's going to be negative 3 everywhere on this line. So the derivative, which is the slope, is always going to be negative 3. So a linear function graph is going to have a constant derivative function graph, because the slope of a linear function is always going to be a constant value. So the graph of a linear function is always going to be a horizontal line or a constant function. This line is decreasing everywhere on the interval, so its slope must be constant or a horizontal line everywhere on the same interval. Derivatives of linear functions are always going to be constant functions. So derivatives are always a degree less than the original function because of that power rule. So a degree less than 1 is just going to be this constant number. Let's take a look at a slightly more complicated example. What if we have a quadratic? So now we got the function x squared minus 4x. And we could find the slope at any point by finding the derivative of that function. So the derivative is going to be 2x minus 4. So the slope is going to be changing, but it's going to be changing in a linear fashion. So again, 1 degree less than a quadratic function is going to be a linear function. So the derivative graph of a quadratic function is going to be a linear function. The quadratic function here in pink changes its slope. It has a decreasing interval. Then it stops. It actually has a 0 derivative right there. And then it has a positive slope on that interval over here on the right side. So f of x is decreasing on the interval from negative infinity up to right here at 2. And then it switches to increasing on the interval from 2 to positive infinity. And right there at x equals 2, it actually has a slope of 0. It's going to have a horizontal tangent line. And we can actually find that out. If I plug x equals 2 into my derivative graph or derivative function, I get 0. So again, derivatives of quadratic functions are going to be linear functions, or the slope of quadratic functions is going to be a linear relationship. So when the quadratic here on the left is decreasing on this interval, take a look at the values of the linear function here. When f of x is decreasing on that interval up to 2, my slope values are negative. The outputs of this linear function are negative. So when a function is decreasing, its derivative is negative. That makes sense. Right here, as we pass 2 and go off towards positive infinity on the x-axis, my function is increasing. So I should have positive slope values, and that's actually what happens in my linear function here. I pass 0 and I start to have positive values on my derivative graph. And right there, when x equals 2, my slope value is actually 0. So I have an output of 0 on my linear graph, or the derivative graph. So wherever a function is decreasing, its derivative graph is going to be negative, or have negative values or negative outputs. Whenever a function is increasing on an interval, the derivative or slope values are always going to be positive. And whenever you see a horizontal tangent line to a graph, that derivative value is going to be 0, or the slope will be 0. That's how we can kind of estimate things for the following examples. So here we have a function, and we want to try and match these four graphs down here as the derivative of this original function or graph. So taking a look at this original function, which of these four possibilities are the derivative graph? Let's compare some slopes here. Right here in this spot of my graph, I'm decreasing, so I should have a negative slope or negative outputs on these graphs. Then right here I have a horizontal tangent line, so I should have a 0 value on my graph. Positive slopes should be a positive output on my derivative graph. Another 0 or horizontal tangent line, and then negative slopes, so negative outputs on this derivative graph. So we have negative values, 0. Let's see, we got negative values to 0 here. We have negative values to 0 there. Negative values to 0 there. D is the only one that doesn't work. Those are positive slope values. We can cross D off and just focus on A, B, and C. So after our 0, we have positive slope, so positive values here. So negative to 0 to positive, that's possible. Negative to 0 to positive values, that's also possible. Negative outputs, 0 and positive, so we're still all good. Then we have another 0 slope right here. So negative 0, positive 0. Well, that takes away A because we don't come back to 0 again. Negative, positive 0, that could work. Negative, positive 0, that could also work. So the last thing we need to look at is what is happening on this part of our graph. We have a negative slope, so we should go back to negative outputs here. And this graph does not go back to negative outputs. So C would be our best guess as the derivative graph. And sometimes you may actually be able to guess because you know what functions look like. This is actually a cube function. And so the derivative of that would be a degree less, which would be a square function or a quadratic. And since this is decreasing, I know that my quadratic will be facing down or concave down. So another way that we can kind of take a shortcut without comparing slopes, just knowing our function types. Let's do one more example. So here's our original function, and we want to choose which of these four best represent the derivative graph. Let's think about our slopes. We have a low positive slope right here. It's not very steep. And then it gets really steep right here, but still positive. So small positive slope to really big positive slope. Let's see which of our graphs do that right off the bat. Well, this has negative values right off the bat. That doesn't work. This maybe has positive values if we zoomed in, but then it decreases, so that doesn't work. So A and B seem to be our only options, where we have small positive values to really big positive values. Right here we have a vertical asymptote, so we can't find the derivative at that value. Well, both of these don't have derivative values at that spot, so they're still okay. And then let's take a look at this piece of the graph. We have a positive slope, really steep, so a big positive to a smaller positive slope. Well, this doesn't have positive values, so that takes care of B, so A must be our derivative graph. We have small positive slope values, really big positive slope values, an asymptote, really big positive values to really small positive values. And that matches our slope values on this graph. So compare the slopes, whether they're positive or negative, big or small, or recognize your function types in their graphs. And there's how you can estimate or evaluate graphs of derivatives.